Have you ever just, looked at your hand or the table in front of you and wondered, what's actually holding all this stuff together? Why isn't the whole world just a big floating cloud of separate tiny atoms? Well, the answer is this incredible, invisible force, a sort of universal glue that builds our entire reality. And today, we're going to figure out exactly what that glue is, the chemical bond. So let's get into it. For ages, this was one of the biggest mysteries in chemistry. Why do atoms bother sticking together at all? And why do they only combine in very specific ways to form these beautifully complex shapes? We're going to play detective today and follow the clues to see how scientists finally cracked this amazing case. All right, here's our game plan. First, we'll define this universal glue. Then, we'll uncover the first big clue that explains why atoms want to bond in the first place. After that, we'll see why simple drawings aren't enough and jump into the 3D world of molecules. We'll dive deep into the science of shape, and then, finally, we'll see why this invisible world matters so much in our everyday lives. Okay, first things first, we need to give this universal glue a proper name, right? And there it is, the chemical bond. It's this basic force of attraction that pulls tiny atoms together to build, well, everything, from a simple water molecule to your own DNA. Seriously, without chemical bonds, the universe would just be a formless, lonely fog of atoms. So, what makes atoms want to form these bonds? The first major breakthrough happened way back in 1916. A couple of chemists, Kosel and Lewis, were looking at the periodic table and they noticed something odd. There was this one group of elements, the noble gases, that just kept to themselves. They were super stable and didn't seem to react with anything. And that right there, that was our first big clue. This led G and Lewis to this really powerful idea, the octet rule. He figured out that noble gases are so stable because their outermost shell of electrons is completely full with a perfect set of 8. And that was the motive. Every other atom is basically trying to get to that superstable state by gaining, losing, or sharing electrons until it also has that magic number of 8. And atoms have two main ways of doing this. First up is ionic bonding. This is basically a total transfer. One atom gives away an electron and another one grabs it. This creates charged particles, or ions, that then snap together like tiny magnets. The other strategy is covalent bonding. This is more of a team effort, where atoms decide to share electrons to make sure everyone in the group gets to that stable number 8. Let's take a look at a classic ionic bond, making table salt. So you have sodium, which has just one lonely electron in its outer shell. And then you have chlorine, which has 7. Sodium is more than happy to give that one electron away to get to a stable layer underneath. And chlorine is thrilled to take it because that completes its set of 8. The result? You get a positive sodium ion and a negative chloride ion locked together by their opposite charges. And that's sodium chloride. Now, the octet rule and these dot structures are amazing tools. They let us count electrons and map out the basic connections. But they have one huge drawback. They're totally flat. They're like a 2D blueprint for a building. They tell you what's connected, but they don't tell you anything about its actual 3D shape. And as we're about to find out, shape is everything. Okay, so it's time to upgrade from our flat blueprints. We need a new theory, a new tool that can take us from the flat page into the real three-dimensional world that molecules actually live in. And that brings us to VSEPR theory. Now, I know the name sounds super complicated, but the idea behind it is so simple. Think about it. Electrons are all negatively charged, right? So the different groups of electrons in an atom's outer shell all repel each other. They want to get as far away from each other as possible. And that's it. That simple pushing and pulling forces the entire molecule into a very specific 3D shape. Methane is the classic example of this. You've got a central carbon atom bonded to 4 hydrogen atoms. That means there are 4 groups of electrons pushing each other away. To get the maximum possible distance from each other, they arrange themselves into this perfect symmetrical shape called a tetrahedron, with a precise angle of 109.5 degrees between each bond. But what happens when some electrons aren't actually in a bond? We call these lone pairs, and you can think of them as the bullies of the molecular world. They take up more space and push harder. In ammonia, nitrogen has one of these lone pairs, and it shoves the other bonds closer together, squishing the angle down to 107 degrees. And water? Oxygen has 2 lone pairs. They create even more repulsion, bending the molecule into its famous shape with an angle of just about 104.5 degrees. So, VSEPR theory is amazing for predicting the final shape of a molecule, but it doesn't really explain how an atom is able to make bonds that point in those exact directions. To understand that, we have to go one level deeper into the science. This is the big idea behind valence bond theory. It tells us to stop thinking of bonds as just lines on a page. Instead, a bond is the actual physical merging of what we call atomic orbitals. These are the 3D regions where electrons hang out. When two of these orbital clouds overlap, the electrons can pair up, and that's what locks the atoms together. But this created a new puzzle. If you look at a carbon atom, its basic tools for bonding, its orbitals, are not all the same. It has one spherical s orbital and three dumbbell-shaped p orbitals. If it used those just as they are, it would make a lopsided molecule with different types of bonds. But we know from experiments that methane is perfectly symmetrical. So how on earth does carbon pull that off? The answer is just brilliant. It's a process called hybridization. Think of it like a painter mixing colors. The carbon atom takes its different s and p orbitals and just blends them together. And what it gets is a brand new set of identical hybrid orbitals. These new orbitals are all exactly the same, and they're already pointing in the perfect directions to form those symmetrical shapes we see. So for methane, carbon mixes its 1s and 3p orbitals to create 4 identical sp3 hybrids, giving us that perfect tetrahedral shape. If it only needs to make, say, 3 bonds, it'll mix 1s and 2p orbitals to make sp2 hybrids, which results in a flat, trigonal planar molecule. It's this beautiful, direct link between what's happening inside the atom and the final shape it takes on the outside. And of course, the science doesn't stop there. There's an even more advanced model called molecular orbital theory, which imagines electrons belonging to the whole molecule at once, not just to individual bonds. But that's a deep dive for another day. So we've gone through octets, repulsion, hybrid orbitals, all this amazing theory. But now we get to the most important question of all. So what? Why does any of this actually matter? Because a molecule's shape determines literally everything about it. Water is bent because of those two lone pairs. That bend makes it polar, which is the reason it can dissolve almost anything, and why life on Earth is even possible. Carbon dioxide, on the other hand, is a straight linear molecule. That makes it nonpolar, which is why it's a gas. And in medicine, shape is everything. A drug molecule is like a tiny key. It can only work if its 3D shape is a perfect fit for the lock, a specific protein in your body. If the shape is even a little bit off, the key won't turn. So you see, our understanding just kept getting better and better. We started with simple dots on a page, then we moved to 3D repulsion, and finally, we dug into the quantum mechanics of orbitals. Each theory isn't wrong. It's just a more powerful tool in our toolbox, letting us see the invisible architecture of our world with more and more clarity. So the geometry of these invisible bonds isn't just some abstract idea from a textbook, it's the very foundation of the world we live in. Understanding it lets us design life-saving drugs, create incredible new materials, and truly understand life itself. So the real question is, with this amazing knowledge, what will we build next?